Good. 1 second. Good. Okay. So, good morning. I'm a little bit sleepy, so please bear with me. But yeah, so also this talk, we're going to try something new that I haven't tried, so it may not work as well as I expect, but we'll see, okay? So, first thing, this is going to be an interactive talk, so please, if you have a cell phone, you can scan that QR, or if you have a computer, just go to supersymmetriclido.com and enter that number, and then we continue. You will have the chance to join later if you miss this one, okay? So, just to have a summary in one slide, can you see okay, or is there too much light? Can we lower the light? Maybe. Okay. So, well, these things, dark matter in one slide, okay? So, you've been hearing, I think, all week that there is a lot of experimental evidence of dark matter, okay? There are lots of observations that we cannot explain unless we assume that dark matter exists, and that really motivate us, okay? But this extensive evidence, it's all linked to gravitational interactions, okay? So far, that's the only thing that we have. Many different kinds of observations from large-scale structure, the abundance of the different elements in the universe, but, oh, nice. Okay, but all of that is in a way linked to gravitational interaction. So far we don't know anything more than that about dark matter. So although we know a lot about where dark matter is, how it is distributed in the universe, how much dark matter is around us, we don't know about anything about what is the microphysics of the dark matter, how it interacts with other stuff, and how it interacts with itself. We have some hints that you have been probably hearing about, but we do not know anything in detail, okay? The other thing is that you've probably been listening all week, hearing all week, is that there is a general consensus that we can talk about dark matter using the particle physics language, which it's not, I mean, it's not a given, okay? But it's something that we will assume here. So we can use Lagrangians, fields, particles, and all the things that we know about that, okay? Direct detection, that is what I'm going to talk about, requires that dark matter interacts with standard model particles through other channels that in addition to gravity. At some point in technology in the future, we may have gravitational detectors that are sensitive enough to just directly detect dark matter, but so far, no luck, okay? So this is a really big assumption. We do not know if this is true or not. I mean, this may be false, and then we will never detect dark matter directly. This is a possibility, okay? So you've probably seen this many times. I'm going to talk about direct detection. This means that we have a standard model particle, a dark matter, something happens, and then you have energy transfer between the standard model particle and the dark matter in some way, and then you observe this one and you don't see this one, but you see the effect directly in standard matter. We, in a way, already do that when we see the gravitational effects of dark matter, okay, but we are looking for other effects that in addition to gravity. In colliders, is in this direction, okay, you just make two standard model particles cross each other, and then you have some hopes of producing dark matter, okay? And there is a separate lecture completely dedicated to collider experiments. But in many times, direct detection and collider experiments are compared, and I'm going to spend a little bit of time talking about this. Regarding indirect detection, you've heard, I think, a lot of this last week. This is essentially astronomical observations and how things affect the observations from, heavenly bodies that we have, okay? But I'm going to focus in the comparison between these two. So many times you will hear from the direct detection people or from accelerator people that, what the other team is doing is completely nonsense, that the comparison is not fair, and usually they both are correct, okay? So the situation with production at colliders, what you have is that you have, well, let's say you have LHC, so you will have two quarks or gluons, okay? And then you have a coupling constant, you create a mediator, and then this mediator decays into two dark matter particles. This is one channel. I mean, there may be other channels, but this is a very nice possibility, okay? So what you have is that the cross-section for producing this, although I'm not doing the full calculation, essentially it scales with the square of the product of these two coupling constants, that they don't need to be the same, okay? So if one of them is very small, then this will be highly suppressed and you will not see that in a collider. On direct detection, you are looking at a very, very different energy scale. Here, what you have is that essentially you only are looking at an effective theory from very far away, very similar to the Fermi theory for neutrino interactions, okay? You are looking at this, you don't see the mediator, you just see the energy transfer between a dark matter particle, a quark, and then the end result. And this thing, when you do the calculation, it turns out that for the spin independent and interacting with the nuclei, you get something that is proportional to this. So in this case, even if one of these things is very small, if the mass of the mediator is very small, then you have a pretty, or you can have a pretty large cross-section between dark matter and nuclei, okay? So these two things are complementary. So they are not looking at the same thing at all. And there is no way to have a fair comparison between these two things without assuming a model, okay? So if we put that together, I'm going to come back to this, but essentially for a large group of theories, what you get is something that looks almost like this, that there is a region where the mass of the mediator is relatively high, but not too high, and that where accelerators dominate, then if the mass of the mediator the mass of the mediator here is small, then direct detection completely dominates. I mean, there is no comparison between just orders of magnitude better. And also, if the mass of the dark matter particle is very small, you are in this territory here, that is what we call the axion land, where you have things that look more like a field, because the mass of the dark matter candidate is so small that these things have like a large wave function, okay? So, and you are also here not looking at production in accelerators, because the mass is so small that you will never see this in, for example, a missing energy search, okay? And here we have all our favorite candidates, WIMPs, dark photons, SIMPs, whatever, okay? And we will talk about this a lot. But going back to the comparison between direct detection and accelerator searches. Here is a plot from this year, okay? This is a CMS result in which you have different searches looking at different channels of production in the LHC, and then you have these lines that are exclusion plots that are coming from that, from those analyses, okay? Here you have not what typically is shown for accelerators, because in this plot they try to put together accelerator results and direct detection results. Direct detection results are these lines here, okay? This is Xenon, LC, Panda X. All of these lines here and this one are accelerator results. Sorry, no, direct detection results, okay? And these lines are accelerators. So when we do a direct detection search, okay, as we mentioned before, we are placing a bound, or we are sensitive to the overall cross-section between dark matter and the nuclei. And that's what's in this y-axis, okay? But that's not what accelerators can see. So in order to translate these two things and put them in the same plot, they did some assumptions. So those assumptions are here. If we zoom in, you see, well, they assume a value for GQ, that is the coupling constant with the mediator, and some assumptions with the coupling constants for the dark matter, which are pretty numbers, but you can pick whatever you want, okay? And if you move those numbers, these lines are going to move like crazy here. So essentially, well, yeah, this is a result that is valid for this particular choice of coupling constants, but that's it. So these comparisons are usually not very informative. So just, and these things are buried in there. So it's very easy to miss them, okay? So just have in mind when you are looking at comparisons between direct detection and accelerator searches that they may not be as meaningful as they seem, okay? So just to wrap up, okay, there is no model-independent way of comparing direct detection searches and accelerator results. But the thing is that these two things are looking for different stuff. And right now, as we don't know what dark matter is. We don't know anything about the microphysics, or we know very little about the microphysics. So we need to explore as many options as we can. And these two things are looking at two different lands. If we are extremely lucky, we have, I mean, nature will provide us with a candidate that we can see in direct detection and that we can produce in a collider. But that's not guaranteed at all. So we may just have one of them, okay? And if we don't have a proper signal to chase and we don't have any information about what we are looking at, there is just no point in comparing these two things. At least that's my view, okay? So now, going back on direct detection. So yeah, you've seen probably this a lot, okay? 80% of the matter is dark, but yeah, why? I mean, we haven't seen it. Why is it so difficult, okay? Are we completely dominated by dark matter, but then nobody sees it, okay? So just to put some things in context, well, this is a picture of our galaxy taken from outside. We are around here, okay? And this glowy thing is the dark matter halo. Last week you've heard about dark matter halos that are essentially spherical or kind of, okay? More matter in the center, more diluted when you go outside. Then we have our solar system, and we have some dark matter around us. But again, it's not condensed in stars, or at least that's what we believe, that there are no such things, or it's at least the universe is not dominated by dark stars or clumps of dark matter that are very compact and dense. So essentially, this is all fuzzy and distributed around us. So when we look at the Earth, essentially we are looking at just a point here, and we can compute what is the dark matter density around us. You've already seen that number, probably is this. And now it's the first interactive question of this talk. So how much dark matter is contained in the volume of the Earth? Okay? And your turn. Let's see if this works. So this is the dark matter that we have direct access to. Okay, this is the only dark matter that we have any hopes of. Oh, it's not showing online. Okay, have you voted already?
It's shown in the pause tab in case you didn't find it.
Oh, okay, too bad. Okay.
No, it's good.
Okay. Well, keep voting. So I see that more votes are coming. Okay, so we'll wait a few more seconds, okay, but this is the only dark matter that we have any hopes of directly detecting, and how much it is. Okay, so if we look at this, oh, everybody knew this. Oh, well, not really. Not really. Okay, so stop voting. Right now it doesn't count. Okay. So what you can see, about 1/3 of the people now, I mean, some people is cheating and adding more to this, but about 1/3 of the people here thought that it was about 0.5 kilogram. But then we have, things that go from 1 order of magnitude more to many order of magnitudes more or less. Okay, so this is a number that is, I think, again, it's not super meaningful, but it gives you an idea of the scale of the problem. Okay, so we are looking for 0.5 kilogram of something that is spread in the whole volume of the Earth. And the situation is a little bit worse if we restrict ourselves to just the volume where we can actually look for stuff that we have access as humans, and in this crust, it's only 2 grams. Okay, so we are looking for 2 grams of stuff in the whole world. This is diluted, in principle uniformly distributed, and this looks really bad, but let's compare this with something that we can definitely see. So we have cosmic rays. This is not a cosmic ray schools, but you probably know that there is radiation coming from space that is hitting us, and we can definitely see it. For example, we have auroras. We don't even need any instruments to see cosmic rays. This is pretty simple to detect, a lot easier than dark matter so far. So what's the mass of all the cosmic rays that hit us? So the cosmic ray density in our neighborhood, it's about 1 eV per centimeter cube, okay? And that is orders of magnitude smaller than dark matter, okay? So in the region that we have access, and also that cosmic rays have access, because not all the cosmic rays can go inside the volume of the Earth, it's 7 nanograms, which is a lot less than what we had for the dark matter. So instead of having 2 grams of things that we are looking for with cosmic rays, we just have 7 nanograms. So there is a clear advantage to dark matter, but still we don't see it. So what's the problem with dark matter? Well, the problem, of course, is the channels through which it interacts, or the cross-section. So cosmic rays, most of them interact with standard model particles through electromagnetism, which is one of the strongest forces around, long range and everything, super pretty, and we don't know what is the way that dark matter interacts with standard model particles. So here we have just a way of picturing how much smaller the cross-section for dark matter has to be with standard model particles to be in the situation that we are right now, essentially that we don't know what it is and we cannot detect it directly. But now it doesn't look so bad. I mean, we need to just make a little bit better detectors, and maybe we can see it. So, dark matter candidates. As I said before, we don't know what the microphysics of dark matter is, so there is essentially the full range of masses that is allowed, and covering that you have many, probably thousands of variations of different theories that I am grouping into 3 big sets. One is the standard WIMP, that essentially is something that you've been hearing a lot. Then there are the new kids on the block, or newish kids on the block, that are the light dark matter models that are essentially, things that are pretty old actually, but that are dark photons, supersymmetric partnered SIMPs, or other stuff that populate this region here, but that don't have to have the mass that we, in the past, historically we have assumed for the WIMP, just to have the WIMP miracle that you heard last week about. And then this here is also the bosonic dark matter, that we know that essentially if dark matter is very light, it's most likely made of bosons. So the theory predicts here that we are looking for particles that behave like bosons in order to be able to produce clumps. If not, the exclusion principle just doesn't allow you to collapse to something that looks like a halo. And in here, we have the axions, but also other candidates here. And in this full range of masses, of course, we will need to come up with a lot of different experimental techniques if we want to be able to detect these things. And each of these experimental techniques will be tailored to different characteristics of these candidates. Okay? And before we go into that, this is just a cartoon plot of a typical exclusion limit that you get from a dark matter search. Okay? So here we have the dark matter mass, and here we have the cross-section between the dark matter and the standard model particles. And what you have is that there is typically a sharp improvement on the power of the limit. So you have a more stringent limit. This is the region that is excluded. And then what you have here is that it slowly rises when the dark matter mass goes up. Okay, and now this is a general characteristic of all the direct detection searches, and the question is why? And this brings us to our second interactive moment of the talk. Okay, this one is a little bit different. You have to write down whatever you think it is in the most compact way. Okay, and we will see that here. So maybe, I mean, in principle, if you already scanned this, it's the same thing, okay? So you can just go back to the previous link that you had already opened, and now it should show this question. By the way, this is just a channel for you to loss of sensitivity, okay? Why? This is a complete anonymity. You can say whatever. Less particles, okay, I like that. Why? Magic, okay, good. Okay, so yeah, here we have essentially the answer to that. Okay, so we said at the beginning that we know what's the density for dark matter in our neighborhood, and that is fixed. So if we have heavier particles, we will have less particles. And that can be pretty dramatic, as you can see here, okay? If you start with milli-electron volt mass for the dark matter candidate, then you have 10 to the 12 particles per cubic centimeter. On the other hand, for a TeV, well, you really need something big. You have 15 orders of magnitude less particles there, okay? So what this means is that the detection techniques are going to be very different when you are looking for things in the TeV scale, when you are looking for things that in a milli-electron volt scales. And as a general rule, sorry, I'll go back. So, and now we will discuss essentially what that means as a general rule, okay? So just this to go quickly, the other part that goes up, anybody knows why? What's happening there? Why do we have that sharp increase? I don't have another interactive moment because if I have more than 3, I have to pay, so I only have 3. Okay, so this sharp rise, why is that happening? Do you know? Well, that's just the sensitivity of our detectors, the energy threshold, essentially. When you have a candidate that has a mass that is smaller, just by kinematics, even if the cross-section is big, okay, just by kinematics, the amount of energy that it will share with the standard model particle will be much smaller. So you will need a threshold, an energy threshold in your detector that is smaller and smaller. And that's what we are seeing here. When you are getting to that energy threshold, you start losing all your sensitivity to any, and you don't have any chance of seeing the dark matter interactions. So that's why we have this sharp increase there. So there is a sweet spot around here where we have a lot of dark matter particles and our detector behaves properly. Okay. This in one slide means that essentially if you are looking for candidates that are more massive, you will need a detector that it's big just because of flux. You will need a big detector. You cannot get away with a small detector, even if it's a super duper ultra sensitive detector, you just don't have the flux. And this is something that sometimes is lost in limits, okay? I mean, you can keep drawing that line up as much as you want, but at some point, you are talking about something that has an expectancy, even for a cross-section of 1. I mean, 100% chances of interacting and seeing it in your detector, that is 0, okay? So, although you can place limits for those candidates, they are not real limits. Statistically, they don't make any sense because the expectation that you have is 0 there, okay? You don't have enough flux. So be careful when you are extending the reach to the right of your direct detection search. So yeah, here we will need massive detectors that are big, and for this region, we don't need that. I mean, of course, if you have more, it's good, but you don't need that anymore, because now the flux is not a problem. You have plenty of particles there, okay? But the cross-section may be very small. Still, you will be able to place very constraining limits or have an experiment that is highly sensitive, even if the mass is small. So an experiment can have 15 orders of magnitude difference in size and still be have the same sensitivity for 2 different candidates, okay? So be mindful of that too. But this is already giving us some hints about how to design different experiments depending the mass that we are looking for. And I'm going to group this into these 3 groups, as I mentioned before. The standard WIMPs, the typical way of looking for standard WIMPs is through this interaction channel with standard model particles. That is the coherent nucleus interaction. And the reason for this, you also have here this from neutrino detection, is that you have an enhancement. These things are low energy, so the interactions are all low energy, so these are coherent interactions between the dark matter particle and all the nuclei, all the nucleons in the nuclei. And that has a huge enhancement when you consider coherent effects in big nuclei. Okay, so you want to have something here that has as many nucleons as possible. You want a heavy element there for this to enhance your probability of seeing that. At the same time, we would like to have the ability to discriminate between nuclear recoils and electron recoils, because many times, for example, when you have, a typical radiation detector, the vast majority of what you are seeing there are the interactions of radiation with the electrons in the outer shells of whatever material this detector is made of. And those are electron interactions. So you are overwhelmed by that. That's your background. You are not interested on that channel if you are looking through this interaction channel, and you would like to have a way of telling these 2 things apart just to reduce your backgrounds. It's not mandatory, but it would be nice. Then, as I mentioned, heavy nuclei are good because the cross-section is bigger, but the problem is that the bigger the thing is, the less energy transfer you have. So this is just kinematics. If things are very mismatched, you are hitting a bowling ball with a ping pong ball. You've heard this, okay? So, and in particular, if you are looking at light dark matter candidates below 10 GeV, you really need lighter nuclei, but then you don't get enhancement, so it's a trade-off there. The typical targets for these things are noble gases, where you have things that are very heavy, like xenon. You have things in the middle, like argon, okay, in which you get a lot of enhancement, but still you can handle those things. And one thing that is also very important that I did not add it here is that, and that's important for almost all of them, but in particular for this category, is that you have a way of eliminating all the radioactive isotopes on this thing, or dealing with those. With argon, that's a big problem, okay? There are naturally occurring isotopes of argon that are radioactive, and then if you don't have a way of suppressing those, you just purify your argon, and then you have a lot of argon that is radioactive in your detector, and of course you have a very large background. So all those considerations go into this category. Then we have light dark matter candidates, okay? And in this case, we will be replacing the nuclei as targets with electrons that are much, much lighter, okay? The reason for that is just kinematics, what I said before. And ideally, we would like materials that have a small band gap. That means that it's easy to transfer energy to one of the electrons in the material, okay? But the problem is that if this band gap is too small, let's say, for example, metal, then you have continuous excitations just for thermal reasons. Thermal excitations of things that move around and that produce a lot of dark counts. So you want something that has a small band gap, it's easy to transfer energy to, but at the same time that you can control how many dark counts you have there due to thermal excitation, for example. So, and you will see, we will discuss all these things in detail during this week, that the good targets are, again, noble gases, or noble elements, also cryogenic crystals, and semiconductor detectors. These have typically small band gaps or band gaps equivalent, and they will provide typically the better sensitivity. And lastly, here again, we are in axion territory. We have, again, a large range of masses because we are going from milli eV to eV or even keV, depending on what you consider there. So the techniques that we will be using here are things that have excitation levels that are very, very small in the order of milli eV and things that are in the order of eV or keV. And that is semiconductors for eV, and then resonant cavities or antennas for the lowest energies. Putting all that together in one slide, we have this, okay, and we will be revisiting all of these different techniques and categories during the week. But to start, we are going to use something that I did not focus specially, but is scintillating crystals. You already know about scintillation. I've heard from the previous talk, okay? So why I'm focusing on this technique to start today in the 20 minutes that I have left, it's because there is an experiment that is called Dama Libra. Probably you've heard about this thing that has a signal, okay? I will talk about this. And although there are many reasons why the consensus in the community is that this is not a proper signal, it is still very important to discuss it, I think. The technique that they use is very simple. Essentially, they have a crystal that has scintillating capabilities. And this crystal is a sodium iodine crystal that has some thallium in it to improve the light production properties and also the mechanical properties. And this is just a scintillator. So the targets here are sodium, iodine, a little bit of thallium, but much less than all the other stuff, and the electrons on these three elements. So those are the targets. So you are expecting that the dark matter will interact with one or more of them, deposit some energy, and that will produce excitations in the electrons in the crystal, and then when they de-excitate, they produce light, and you see that light. And typically for this type of crystals, you have something that they produce about 50 photons per keV, and you try to detect those, coupling these crystals to a light sensing device, in this case, a photomultiplier tube. Actually, in DAMA, they have two photomultiplier tubes looking at the same crystal to improve the light collection and also to have some vetoing capabilities between coincidences on both PMTs at the same time. So the technique is very straightforward, and this experiment has been running for many years. And the thing is that, well, let me show you some pictures that will be important overall. So here is one of the photomultiplier tubes. You see it. This is the window of the photomultiplier, and it is encased in a copper tubing, okay? And that goes into one of these modules. Inside this rectangular volume, there is a crystal, okay, a sodium iodine tellurium crystal, and then you have one photomultiplier tube at each end. These things are coupled to the crystal, and you collect the light that is produced in that one. And then these modules go inside a big copper shielding, and they are stacked all together in like a Lego-like thingy. And when this thing is closed, the shield is closed, they look for interactions in that thing. This is operated also underground to reduce the amount of cosmic radiation around. And look at this person. He's wearing a very uncomfortable suit. And the reason for that is twofold. One, and the main, is that it's something that you will hear all week. All these experiments need to be clean. How clean depends on the technique that you are using, but essentially they all need to be clean, and clean means not having any radioactive contamination. And what do we mean with radioactive contamination? Well, we are all radioactive. Radioactivity is all around us. There are naturally occurring isotopes that are radioactive of a lot of elements. And if you just pick something and take it underground, you will have a lot of radiation, typically. So you need to pick materials that are easily purified. And when I mean purified, is that you are able to eliminate all the radioactive isotopes from the element itself and also from other things. Sometimes chemically it's very hard to separate different elements, and one of them is radioactive and the other one is not. So you will be seeing that copper is used a lot for dark matter experiments. The reason for that is that copper is one of the things that we know how to purify best, together with silicon, maybe. And when you purified copper, you do this. There are different techniques, but essentially you are removing. You are removing all the radioactive contamination in that, mainly from naturally occurring isotopes of lead, uranium, and other stuff. There are no naturally occurring isotopes that are radioactive for copper, so that's great because it's very hard to do an isotopic separation of stuff. If not, we would have nuclear bombs everywhere. So that's a reason why we use copper. So this person is essentially protecting the system from contamination, and also the sodium iodine crystals are hygroscopic. That means that they tend to absorb water and they get damaged. So all these things are encapsulated, and everybody there is very mindful of the level of humidity. So when things are stacked in Dama, it looks like this. So you have outside layers of shield made of polyethylene and lead. The polyethylene is there to stop neutrons that are coming from the walls in the cavern where Dama is placed. Then the lead essentially is to stop all the gammas. And then the copper shield is to stop any contamination in the lead shield, essentially, there. Okay, because you can purify this a lot. Copper is not as good as lead in stopping gammas, but you can make copper super clean. So that's why you have inner shields that are made of copper. And it's a big experiment. It's 250 kilograms of extremely radio-pure crystals, and I will come back to this in a few slides. The threshold, it's about half a keV, which is not terrible. And they have been running for a long, long time. So they have collected 22 annual cycles, full annual cycles of data, which is an extremely long total exposure of about 3 tons a year, which is a lot. We will compare this to other experiments soon, but this is a lot. So all that, great. So Dama, it's an awesome detector. Really, it's impressive, okay? The thing is that when they turn this thing on, they see events, okay? Which is not uncommon. They are looking at all the radiation. You still have some remnant cosmic background going. Yes?
Can you back the?
Yes.
Please. Can you see me?
Yes,
Okay.
a little bit, yes.
How do you close the layers? I mean, it's a closed square, right?
Yes.
And a cube. And how do you close the layers? I mean, with glue, with...
No, they are just stuck, or screws.
Okay.
High purity screws, yes.
So just put...
Put
and-
together, yes, yeah. Put together and that's it.
Okay, thank you. It's just like that.
I mean, the crystals themselves, they are glued to the photomultiplier tubes. I mean, there is some gluing interface just to have a better transmission of light efficiency there, but all the other things are all welded or just standing there or with high purity screws.
But there would bring contamination,
Yes.
right? Even
Yes.
glue.
Yes, so anything that is used has to be carefully selected, and that is true for all the experiments that I will be talking about. Even, I mean, yeah, the glue that you use for a cable, the material that you use for the insulation in a cable, everything needs to be screened. And that's a pain. So, yeah.
And everything is made in a kind of a clean room?
Yes, so depending on the cleanliness level that you are aiming for, things are handled inside clean rooms. Sometimes they are also handled in volumes that have a nitrogen purge. So a closed, sealed volume where you are flowing very clean nitrogen. And the reason for this is that one of the main sources of contamination is radon. Radon decays and produces radioactive isotopes of lead and other stuff that can stick to whatever surfaces you have and make your life miserable. So, and they are, I mean, it's floating all around us. We are breathing radon right now. So in order to really mitigate that, you need ultra clean volumes in which you do that. I mean, that is absolutely true for most of the big detectors. When you are looking at the smaller detectors that look for lighter dark matter candidates, you can get away many times with a lot less cleanliness. And I will discuss that during the week.
Okay, great.
Okay. So as I was mentioning, they turn this thing on and they do see something. So what you have here is just the rate of events that they see as a function of the time of day, essentially. Okay, so many days. And this is counts per day, per kilogram, per KeV in crystal 1. So this is one of the many crystals that they have, and this is what they see. Okay, pretty stable, and about one-ish count per day per KeV per kilogram. Okay, that's what they see. This is not exactly the same in all the crystals, but roughly it's what they see. So when you have a signal, well, this does not mean that this is a dark matter signal at all, and they do not claim that this is a dark matter signal. Okay, when you have a signal, well, you need a model for the background. Okay, if you don't have any signal, yeah, you don't need to worry. That's it. But now, if you have a signal, then you need to understand what is your expectation for the background in this experiment. And to do that, well, you can have a very detailed simulation using, for example, GEAN4 or other tools that allow you to propagate particles in your detector, measure what is the remaining radioactive contamination in the materials of your detector, and then extrapolate that to what you expect to see in your sensor, try to estimate what's the contribution from cosmic rays and environmental background. Or you can do another thing, that is what DAMA is doing, which is very clever. I mean, they did not come up with this, but this is something that they are using. Essentially, the idea is that, well, this is again a picture of our galaxy taken from outside, not really to scale. So this is the center of the galaxy, the solar system, and the solar system is moving around the galactic center. Then you have that the Earth is rotating around the sun. So sometimes this movement aligns with the direction of the movement of the sun around the galactic center, and sometimes it's in the other direction. So what that means is that essentially our dark matter halo that is surrounding us, that it follows a Maxwell-Boltzmann distribution you've heard last week. So that doesn't have any preferred direction in this radial coordinate. Yeah. So the end effect is that you have a wind as seen from the sun, the solar system, and then that sometimes when you are aligned, the wind is stronger. When you are anti-aligned in December, the wind is a little bit weaker. So you expect to have an annual modulation effect, because essentially dark matter, as observed from the solar system, has more kinetic energy in June and less in December. Okay? And that's what they see. Okay, so this slide here is taken from IDM, that is one of the biggest conferences in dark matter, that was last week. And what you have here is the cumulative results from DAMA, taken from these 22 annual cycles, okay, put together. The data at the beginning with the older detectors was a little bit worse, and now it's very clean. And what they see is this very nice daily annual modulation that is beyond any statistical doubts. I mean, this is 12 sigmas or more. I mean, yeah, 13 sigmas already. So, I mean, the chance probability of this is 0. The question is, are there any systematics? Are there any problems with the analysis? Are there any other things that can give you an annual modulation? Yes? Yes, the black line is a fit. Yep. And yeah, here what they say is we fit the data points and we compute the modulation size, so the intensity of the modulation, also the phase. And the phase matches pretty close to what we expect from what I said before, that in June you have a maximum and in December you have a minimum, which if this was just by chance, you would not expect that to fit, okay? So there is a lot of puzzling information there. And the thing is that at this point, this is not I mean, you would say, okay, we have this, then why is not everybody just looking at this data or doing other stuff because we have already discovered dark matter? The question for that is not trivial. It's more sociological than physics, but the reason is that DAMA has been very obscure on how they do the analysis and what are the systematics that may be associated with this. The data has never been opened or not fully opened for outsider inspection, and other experiments that are trying to replicate this signal using other technologies, that is not sodium iodine tellurium crystal technology, have never been able to see anything like this, and we will discuss how different interpretations of this are just not compatible with the results from other experiments. But the key word in what I say there is interpretations. So if you really want to be able to check this result, you need to use exactly the same technology, because there may be some very unlikely reasons, but still not ruled out reasons, why you may see something in this particular crystal and in no other element or crystal in the world. It is very weird, but I mean, weird things can happen. If not, I mean, just look at the last 3 years. So, yep. Okay, that's also very important. So they collect data, okay, and they can reconstruct the energy of the particle just by looking at how many photons they are seeing, okay? So then they select different regions of energy, okay, to look for modulation. What you would expect is that for the high energy, you don't see any modulation, okay? Because at high energies, essentially these 30 kilometers per, I mean, this small difference, oops, okay. This small difference in the wind speed will not make any difference in how likely you are to detect something or not. But if you are looking at the lowest energies, then you would expect that this modulation increases, because now this 30 kilometers per second, that is a big fraction of the total kinetic energy of those, of the particles that have that energy, okay? So, and they do that analysis, okay? So they bin this thing in different energy bins, and they see exactly what I said, okay? That you see a bigger modulation for the low energy bins and a smaller modulation or no modulation for the high energy bins. And they provide the digested data. They do not provide the raw data or background data. I mean, it's very, very obscure what they do. But they do that. And this 2 to 6 kV selection cut or window, it's it's the magic window that they pick, okay, in which the significance is biggest, but there is no physical motivation behind this. Again, there is no wrong, that's nothing wrong with looking at this, because we don't know what dark matter is. But so far the only this doesn't have any meaningful reason why to pick that window other than that's what they use, which will become important for what I'm going to discuss next. So I'm out of time. I don't know, should I stop here and continue next week, or 5 minutes? Tomorrow, yes.
So if 2 minutes would be okay. We're running 5 minutes later. Right. Okay.
Okay, well, I'll move quickly here, so to finish with this. So the what I said before. So there are many other experiments. So this is Dama Libra, okay, what I mentioned before. There are all of these experiments. There are even more experiments doing essentially the same experiment as Dama Libra. So using sodium iodine crystals with different variations, some clever variations. I don't want to go into detail there, but essentially they are all doing the same experiment. The problem is that Dama Libra is big, okay? So if you really want to cross-check it, you need a big experiment. But also the signal is so large that you don't need really a super big experiment, because even with a smaller experiment, well, maybe you don't get 14 sigmas, but I mean, you don't need 14 sigmas. With 5 sigmas, we would be fine. So you can have smaller experiments. But this is what is maybe the biggest problem around, is that Dama Libra has super clean crystals. So the quality of the crystals that Dama Libra has is unparalleled. No one has been able to replicate this. And one of the reasons why is also linked or one of the reasons why a lot of people dislike Dama Libra. And the thing is that they hired a private company to do the R&D for producing the ultra clean crystals. They paid for this with rule that said that this company could never ever sell these crystals to anybody else. So they did that. The company said, okay, they produced these incredible crystals, and then because they cannot sell these crystals to anybody else, they fired the people that did this, and that people doesn't work anymore in the company or in the field. So it's essentially impossible to reproduce exactly what they did. Okay? But there is a lot of effort in producing super clean crystals, but so far these are still the best ones. Others are very close to that, even better in some of the metrics, but still Dama Libra has some advantage there. There is the runner-up, there is cosine 100 experiment that also presented results last week. And we can talk about this in the coffee break because I don't have any more time. But essentially, here they pick 2 energy windows, like Eliana asked, okay? And they look, okay, if the modulation from Dama is what they are claiming, what should we see? And this is, so the x-axis is the amplitude, so they expect to see some amplitude in the data that they would take, and this is what they see. So they see something that is compatible with no modulation at all, 0. And the difference between these 2 things is 3.5 sigmas, okay? Which you say, okay, it's still not rejected, but it's close to being rejected. The issue here is that, well, this is in these energy windows. If you look at the magic energy window, 2 to 6, it's smaller. Okay? Again, this is most likely by chance, but still it's there. Okay, and I'm going to finish with this. So both, and I'm done. Yeah.
Okay, let's thank Javier. Right. We had one pessimistic vote. 2. So we have time for 2 questions. Yes.
Hi. So for sodium iodine experiments like cosine or Anais, I know that they have muon veto in the experiment.
Sorry?
Muon veto, cosmic ray veto. Dama doesn't seem to, at least in the experiment, seems to have this kind of veto, since cosmic rays have modulation too. I know that Dama is at Gran Sasso, so there are other experiments that can measure this effect, but since Dama don't have this kind of veto in the experiment, isn't it kind of problematic for them?
Yes. So the answer is yes. There are, I didn't go into details, but there are many effects that we know of that produce annual modulation, and also that produce an annual modulation that is close to what you would expect from this June, December, because essentially it's summer and winter and the atmosphere changes, and because of the atmosphere changes, the cosmic ray flux changes, so you have annual modulation effects due to that. There are also even more strange effects like radon that I mentioned before. So it gets kind of trapped in the ground when it's cold, and when it's warm, it's released. So yeah, depending on the temperature, you may have higher concentrations of radon in the area or less. So there are definitely annual modulation effects that can mimic this signal, and that is what the vast majority of the people believe is happening with DAMA. But so far, there is no explanation that you say, okay, yeah, it's this. This works, that's fine. And there are hundreds of papers. So the amount of effort that has been dedicated to this, even not counting all the additional experiments that are running now, it's huge. And maybe it could have been prevented just by opening the data. Yeah.
Okay, last question.
Thank you for the lecture. About the crystals, I mean, the experiment told to the community that there was, the purity was like that. The experiment did that.
Well, I mean, you have many ways of estimating the purity. Okay, so I'll go back, sorry.
My question is just kind of looks too good to be true, you know.
Yes, it could be that they are completely faking the data. I don't believe that that's the case, because they do release, for example, when you are looking at, I don't know, this uranium radioactive isotope, okay? These things produce some high energy X-ray lines, and when you look at the spectrum, okay, you can look for those, and just by looking at how big these things are, you know how much uranium you have there, okay?
Okay.
And they do that for the different materials, essentially, okay? And they do release some of that data. So unless they are completely faking everything, which, I mean, it could be, but it's I don't know, I think it's not the best explanation yet, but we are getting there. So the community typically believes that the crystals are these high quality crystals.
Okay, and the experiment is in Italy, right?
Yes.
And they are from the government?
Yes, they are mostly, yeah, they are funded by the government, yeah, scientists.
Yeah. I'm just trying to understand because it makes no sense. But,
No, I agree. I mean, a lot of people have said things in that line. Okay, I mean, the government should stop funding unless they open the data. And also at this point, what's the meaning of keep running and keeping things closed? I mean, there is absolutely no gain. You would just give the keys of your experiment to other people and say, okay, just check everything and give me my Nobel Prize. So yes, and that's not happening, and that's also one of the reasons why people don't believe them.
Yeah, it looks like a private experiment. You know, I'm not going to share because I don't know. But
Yep.
yeah. Thank you.
All right, so sorry to stop that, but we are running late, and I have to give some announcements. So the present sheet is in the coffee break area, so please don't forget to sign it. And regarding the experiments, as you know, you make experiments 1 through 5 will be here. Experiments 6 through 9 will be at USP. So those people that are going to USP, University of São Paulo, will take Ubers. So you will meet me in a point that's shown in the map that Carla shown last week, but is just